Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on amplifier. Okay, so for this video, I'm going to concentrate on the stability circle of an amplifier. Okay, so under this stability circle, there are actually two possible scenarios for an amplifier. Okay, the first scenario will be unconditioned stability, okay, which means that the amplifier will be always stable if they meet certain criteria. So basically, this form of amplifier always stable is basically classified as unconditioned stability. Another condition will be so-called conditioned stability. Okay, remember earlier on I mentioned that under this unconditioned stability, the amplifier will remain stable as long as they meet this criteria. For example, now another amplifier also meet this criteria. However, this amplifier may be stable, may be unstable, so hence we need to have another additional condition in order for them to be stable. So hence this form of design is actually classified as condition stability. Okay, so basically in short, this video, I'm going to highlight the key difference between unconditioned stability and also condition stability. This will be the part 11 series discussion on amplifier. So guys, if you're keen to know more about amplifier, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on amplifier. Okay, so this is my email. If you have any question regards on this discussion, please drop me an email. Okay, or if not, if you want to have a faster response, ask me through the comment. Okay, before I continue, I'd like to urge you guys to help this channel by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly understand what is actually a stability circle of an amplifier. So over here, you can actually see the stability circle of an amplifier. So in short, the stability circle can be used to ensure that the amplifier operates in a stable manner across a wide range of frequency. So in short, when we actually design an amplifier, we actually expect the amplifier to work in a wide range of frequency. And in order to ensure this amplifier is able to perform at this wide range of frequency, we need to ensure that the amplifier actually stable under this wide range of frequency. So in order to ensure they are stable, okay, the primary goal, okay, basically of this stability circuit is to prevent unwanted oscillation. We keep this in mind. Any oscillation basically can be due to positive feedback. Okay, so later on, I'm going to explain what is actually a positive feedback. But in short, if we want to prevent any form of oscillation, okay, we need to ensure that there is no positive feedback. Rather than that, we need to have negative feedback. So basically, this is first criteria in order to ensure the amplifier remains stable. Okay, the stability condition of an amplifier circuit is usually frequency dependent. Okay, since the input and output matching network generally depends on frequency. Okay, so if you have seen my discussion on the impedance matching, okay, basically the input and output matching network, they basically, how to say, when we actually design this input and output matching network, we have the L value, we have the C value. When the different frequency, actually we need to design the L and C value actually different. So in short, okay, under this different frequency, okay, I actually need to design different value of L and C for the input and output matching network. And hence, because of this, as he mentioned over here, the stability condition basically is actually also depend on frequency, since they actually influence the input and output matching network. It is therefore possible for an amplifier to be stable at its design frequency. However, they are unstable at other frequency. So for example, when we actually design this amplifier, it can be remain stable at the wide range of frequency that we actually customize it. However, at other frequency, out of the boundary of the frequency that we want to use, they can be unstable. So basically, this is the meaning of this paragraph over here. A single-stage microwave transistor amplifier can be modeled by a circuit where matching networks are used on both sides of the transistor to transform the input and output impedance Z0 to the source and load ZS and ZL. Okay, so basically this is the microwave transistor. And in order to ensure maximum power transfer, we need to have both input and output matching network. And the key objective of this matching network, okay, basically is to ensure that they are able to transform the input and output impedance Z0. Okay, so this is the output, this will be the input Z0 to the source and load impedance ZS and ZL. Okay, so if you're not so sure what I discussed over here, you probably need to take a look on the impedance matching network here. Okay, so condition for a transistor amplifier to be stable. So as I mentioned, there are actually certain conditions the transistor need to be meet in order to ensure that they are actually stable. So in short, if theta in is less than 1 and theta out is less than 1, okay, which means that negative feedback, they are actually stable. However, when theta in is greater to 1 or any of this situation happen, theta out is greater than 1, this causes the amplifier to be unstable. So in short, in order to ensure the amplifier remains stable, these two conditions must be met. Okay, theta in less than 1 and theta out less than 1. Any condition, okay, theta in larger than 1 or theta out more than 1, this will cause the amplifier to be unstable. So in short, this theta in and theta out actually depend on the source and load matching network. Okay, so therefore the stability of the amplifier also depend on theta S and theta L. Let's do a quick review, okay, on the key concept and the method that we can ensure to achieve amplifier stable. Okay, firstly, as I mentioned about oscillation, okay, and also stability, amplifier can oscillate, okay, if there is positive feedback at certain frequency, leading to instability. Maybe in short, let me paint a picture. Okay, for example, you design amplifier in order to have gain, correct? So basically, if you have a positive feedback, okay, which means that the amplifier will keep on increase. Okay, so how can you expect the amplifier to continue amplify the signal if we are going to have a positive feedback? Okay, for example, positive feedback means that, for example, I design the amplifier to be 1, later on will be 1.1 amplified, 1.2 amplified, 1.3 amplified, and hence, okay, there will be a point that the amplifier will be saturated. Okay, can you imagine this? So basically, the amplifier cannot improve the gain continuously. Hence, once they become saturated, that's what we mean that the amplifier will be unstable. So basically, this is what it means. Okay, so basically, we need to prevent it to be oscillate. Okay, so therefore, if we have a positive feedback, which means that the gain keep on increase, then we have this issue that may lead the amplifier to instability. Okay, stability ensure the amplifier actually operate correctly, okay, without producing any unwanted oscillation. Okay, feedback, okay, as I mentioned earlier on, okay, we need to have negative feedback rather than positive. Okay, feedback can be either positive, okay, positive, they can actually cause oscillation, or negative, okay, which means that they actually help to stabilize the amplifier. Hence, the design of the feedback network is very crucial for stability. Okay, the last one, which is the phase margin and gain margin, they are actually quite similar. So basically, for this phase margin, okay, is basically the amount of additional phase lag required to bring the system to the verge of instability. Okay, for example, this phase margin actually has some number. Okay, so this some number actually will be the cost to cause the amplifier to be unstable. Okay, for example, for this case here, same for gain. Okay, the gain margin is the amount of gain increase required to make the system unstable. Okay, which means that this phase margin and gain margin, we need the number to be as high as possible. When they are high, which means that they are actually much more better tolerance against instability. So in short, the higher the margin indicate better stability. What are the methods to ensure stability? Okay, so first method, we can use the form of compensation. Okay, we can add some component. We can add a capacitor or maybe also capacitor and resistor to the circuit so as to modify the frequency response and also improve the stability. We need to ensure that we need to have a negative feedback. Remember, positive feedback actually create oscillation. We need to ensure that the feedback will be negative. So therefore, we need to properly design the feedback network to ensure that negative feedback at all relevant frequency. Okay, whatever frequency that we require the amplifier to be work, okay, we need to ensure that the feedback are all negative. This actually will help to dampen the oscillation and hence improve stability. Neutralization, okay, basically cancel the effect of parasitic capacitor. Okay, so basically we need to cancel any form of parasitic capacitor. Okay, so basically they can actually potential create positive feedback. And in order to prevent this, we need to cancel away the effect. Bypass and decoupling. Okay, basically bypass and decoupling capacitor, they can actually shun the high frequency noise. Okay, remember what is the purpose of the bypass and decoupling? Okay, basically they create a low impedance, especially C. Okay, for example, the impedance of C is 1 over WC. WC is 2 pi F. So when we actually has a high frequency, okay, when we actually has a high frequency, okay, the impedance actually become very small, and hence this can be a path for this high frequency noise to stable the whatever form of noise, and hence because of this, this can also stabilize the amplifier. Okay, last but not least, in terms of stabilization network, okay, we can add resistor, inductors, or capacitor in strategized place to dampen the high frequency resonance and hence prevent oscillation. So basically, these are all the methods that we can do to ensure stability of an amplifier. Next, in terms of stability of an amplifier again, okay, so the stability analysis basically will be a key part of RF design. Okay, we need to learn the basic of stability analysis. Okay, basically this include how to determine, okay, whether a device is unconditioned stable or potentially unstable or condition stable, basically for this case here. So when we actually design an active RF amplifier circuit, okay, we always start with a thorough stability analysis, so as input and output stability circle on a Smith chart that can indicate whether a device is unconditioned stable or potentially unstable. Okay, so in short, as I mentioned, there are actually two types of stability. Okay, one will be unconditioned stability. Okay, so the network will be always stable, which means that the amplifier will be always stable if we meet this condition, as I mentioned earlier on. Basically, for all the passive source and low impedance, they also need to meet this criteria. In short, if all these criteria are met, in short, basically, if these two are met, then theta in will and theta out will be less than 1. Hence, the amplifier will be unconditioned stable, okay, which I'm going to illustrate on the next page. Condition stability means that the network is condition stable, okay, if this theta in is less than 1 and theta out is less than 1, only for a certain range of passive source and load impedance, which means that the source and load impedance need to be under certain criteria, then it will be stable. So basically, this is what we refer as potentially unstable. Okay, so let's take a look in terms of the stability circle. Before I continue, I'd like to urge you guys to help this channel by like this video. When more of you guys actually like this video will have a higher chances to reach out to a larger audience. So guys, help me by like this video. If you have learned something from this video, please consider to subscribe and turn on your notification bell. Once again, thank you so much. Let's quickly understand the two types of stability. Okay, so basically the first condition will be the amplifier will be always stable. Once they always stable, basically fall under this criteria here. So basically you can see that this is actually the stability circle. So it is not overlap with the Smith chart. Okay, so basically with this part here will be always stable. So hence under this condition, the amplifier will be always stable. On the other side here, you can see that for this condition here, okay, so they will be also always stable, okay, because the output stability circle actually cover the whole Smith chart. So which means that this whole part will be always stable, and hence because of this, you can classify the amplifier to be unconditioned stability, which means that they will be always stable. Next, on the condition stability, okay, the network will be stable, okay, if they meet certain criteria, which means that my source and load need to ensure they are stable. For example, over here, okay, so basically this part will be stable, this part will be unstable, so therefore this part we cannot be used. This is what we call a condition. The Z and the load, the ZS and the Z node need to be under certain value so as to ensure that the whole amplifier will be stable. Okay, so with this, I like to end my discussion. Please help to like and subscribe. Once again, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you.